Welcome back to our heat transfer class, where we are delving into the phenomenon of the exchange of thermal energy between surfaces by radiation. This video was made with the support of Energy. After the radiation intensity, in this lesson we will study some definitions and the concept of blackbody radiation. We will divide this lesson into several parts. The objective is to analyze the radiant energy emitted by a blackbody surface, as well as the radiant energy received from a blackbody surface. Let us remember that the intensity of radiation is the amount of radiation received per unit of time at a point in space, per unit of projected area of the emitter and per unit of solid angle. The spectral radiation intensity is for a given radiation wavelength. The first question to address in this lesson is how to calculate the intensity of the spectral radiation of a black body at a given temperature. Its value is given by the Planck's distribution law. It depends on the temperature of the emitter, T, and the wavelength, lambda. The parameters involved are fundamental constants of physics, such as Planck's constant, h, Boltzmann's constant, kappa, and the velocity of light in vacuum, c sub 0. Spectral emissive power. Let us move back to the definition of radiation intensity. Energy per unit of time that is received at a point in space from a black body per unit of projected area of the emitter and unit of receiver solid angle with respect to the emitter. The spectral emissive power of a blackbody can be found by integrating the radiation intensity multiplied by the cosine of theta and solid angle differential. Recall, from the previous lesson, the expression of the solid angle of a normal differential area with the spherical coordinates. Integrating over the entire half-space above the surface, it follows that the spectral hemispherical emissive power of a black surface is equal to pi times the intensity of spectral radiation. The total hemispheric emissive power is the integration of the spectral emissive power over the entire spectrum. Wien's displacement law. From the relationship between the emissive power and the intensity of radiation, as well as Planck's law, we can draw the emission curves of a black body. Wien's law predicts the wavelength where the emission maximum occurs. Stefan-Boltzmann's law. Once the relationship between the spectral hemispherical emissive power of a black body and the spectral radiation intensity has been established, we can integrate with the wavelength, from 0 to infinity. The result is the area under the distribution curve. And this is equal to the Stefan-Boltzmann constant times the absolute temperature raised to the fourth power. That is, the Stefan-Boltzmann's law. Band emission. Emissive power of a black body in a band of the spectrum. If instead of integrating between 0 and infinity, we integrate between two wavelengths that define the start and end of a band of the spectrum, we obtain the emissive power in the band K defined between lambda 1 and lambda 2. To calculate it, we will first define the radiation function. We integrate the spectral emissive power between 0 and lambda. The radiation function is defined as the fraction of the emissive power between 0 and lambda and the total emissive power. So the emissive power between 0 and lambda can be calculated from the radiation function. If we do this for lambda sub 1 and for lambda sub 2, making the difference, we have the emissive power of a black body between two wavelengths. We obtain the emissive power in a band of the spectrum from the radiation functions. Now what we need is an expression for f as a function of the wavelength, lambda, and the temperature. On the graph, notice how f varies from 0 to 1 and that it takes on a single value for each value of the product of lambda and t. Program this formula into your calculator or find out if it is predefined in the calculator functions.